Hey everybody, we're going to do some inductors this time. So let's take a look at the inductor as a circuit element. And let's take a look at how it responds or how it behaves to starting now with a DC input. So if we go over here, first off, the circuit element of the inductor is a curly set of things, a coil, right? It's what it is. It's a coil, and so it's a curly set of things, like almost like a spring, which is kind of funny, but it's denoted L because it's a self-inductor, and the unit I did not discuss with you before, but the unit of L, the unit of inductance, is called the Henry, which is just an H, capital H. And the typical value of these is in millihenries. It's named after Joseph Henry, which is kind of strange because you would have thought that this is the thing that would have been named after Faraday, and the capacitor would have been named after, well, it doesn't matter. Okay. History, who needs it? So we all do. So let's take a look at this circuit here. I've put in a resistor and an inductor with a battery, and it's a DC battery. And I have a switch here, which is a two, I think it's called a two-pole switch. Anyways, it's got two positions to it. One is if it goes straight across like that, it completes the circuit with the battery in it and the resistor and the inductor all together, which establishes a current in the outer loop. If you look at KVL, there will be an initial kickback from the inductor, kind of like I talked about last time. And once the steady state of the current gets established, the inductor does nothing. Okay. And when I take that switch from there and I put it down to there, darn it. When I put it down to there we go. The switch takes the battery out of the loop. Otherwise, I just short the battery. It takes the battery out of the loop, and it leaves only the R and the L in a circuit here on the right. So if I look at this and I loop around here, what has happened is that the battery being taken out of the circuit has had a major effect on the current. We would expect the current to drop to zero immediately. The inductor, however, cannot let things be that smooth. So, or not smooth. Actually, it is a smoother, really. So I should say it can't happen abruptly. And the inductor says, wait a sec, I need to supply the current required to maintain the flux in my coils. So the magnetic field energy, just give you a quick verbal qualitative introduction to this. The magnetic energy that's stored up in the coils then starts to push the charge, and it tries to push the charge in such a way that it's continued the same way. All right. So the current through the L was, when the switch was with the battery, the current was going around in kind of a clockwise loop around the outside. So the current in the L was going from right to left through it. So the current in the after it closes, it tries to keep that current going. All right. The magnetic energy that it's built up from being in the circuit with the battery now starts to do work on the charges, and as the flux changes, right, that induces an electric field which pushes the charges through the coils, right? It induces this circulating E field in the coils, which pushes charge through the coils, trying to maintain the flux that it had. But its energy is getting slowly drained, so its ability to push the charges is now decreasing. It has a finite amount of energy to to put into getting a current moving. And so eventually, like a capacitor, it kind of quote unquote drains. So it stores energy and then uses that to push charge. And then after a while, it's empty. These are not analogies. I mean, these are analogies that work with the capacitor, but not so well with an inductor, because you talk about a capacitor as being charged up or full or something, right? You can talk about the inductor in the same way, but it doesn't happen. There is no charge stored in the inductor like there is in the capacitor. There is energy, though, like there is in the capacitor. If you concentrate on the energy in the capacitor and the energy in the inductor, and you think about those, you will find the behaviors are similar. If you try to think about the inductor as something like the capacitor, insofar it has stored charge, that's not really going to work. The inductor stores no charge. It's just a coil of wire. That's all it is. Let's take a look at the behavior of this circuit now that I've thrown the switch. To this position, the inductor is attempting to maintain this current. I'm going to call little I because it's changing with time, just like the capacitor current would have done. I will start the switch and loop around with the current. So as I do KVL around this small box loop, I'm going to first run into a voltage drop across the resistor, which must mean that because the inductor is pushing current, I have a voltage jump across the inductor. As we discussed before, the EMF in the inductor is basically this. All right, so if I rewrite this, plus minus L, like so. What I'm doing here is I'm actually pulling a double switch on the negative signs for you without actually saying anything about it. The voltage of the inductor must imitate what a battery would look like. So the voltage of the inductor is the polarity of the inductor would look like that. So as I go across and it says the voltage is minus L di dt, I'm kind of double counting the minus as I push it through here. The minus actually comes about because of the rate of change of the current. Really, I should be thinking the magnitude of the voltage. If you remember what I said in the last video about the signs and the negative signs being an indicator of the direction, I've already got the direction in my plus sign right here. I already know the direction of the voltage. I don't need this minus sign to tell me which direction the voltage is. So really, this should have been a plus L di dt. The problem is I is decreasing. So di dt is inherently a negative, and that's why I'm putting the extra negative in here. So that's why I get the negative kind of quote unquote back, even though I never should have had it in the first place. So it's a bit of a negative sign double switch here. In other words, just in case you didn't catch that, I should not have put this minus. This minus here is not this one here. Okay, it's from the decreasing current. Point being that it's there, and what I'm going to do is solve for what the time behavior of the current actually looks like. So I'm going to zing this thing over to this side, pull that over to there, and then I'm going to rearrange the derivative so that I can integrate it. If I do that, I'm going to get a di over I, I got to have everything with an I on the left side with the di, and that's this. I'm going to leave the minus on the right side, pull the L and the dt over there. And it's going to look like that. And now I can integrate both sides. And I'm going to assume limits of integration. The current is dropping, so it started at some value and is going to some lower value, and time was at some value and went on to some other value. The point being here that the log of the current is minus R over L times a time interval. And the current is initially larger. I naught is a larger number than I. So when I go to look at the log of these things, it'll be the log. See, I got to evaluate this and I didn't, so I should do that. It'll be the log of that. And I want to point something interesting out on here on the right side, and that is that apparently, if I can rewrite this for a minute here. Delta t divided by L over R. Right, like that. If I take the R over L and I flip it over and stick it in the denominator, do you think, why the hell would you do that? That's ridiculous. Yes, but that means that the units of L over R are time. Okay, so that's kind of how henries and ohms are related, right? A henry must be like an ohm second. So just kind of how we had the capacitor, if you remember, RC for the capacitor circuit, we had that. It turned out that kind of became a characteristic time. And here, L over R is going to be the same type of thing. So what I'm going to do is just hit both sides of this with an E, and I'm going to get that something funny's happening here. I naught is larger than I, and that goes over there. I messed something up here. I naught over I. Do I want that? Oh yeah, I've totally messed that up. Why am I doing that? I've got the integrate. Something's funny here. Yeah, because you're writing the limits the wrong way around. Ridiculous. I over I naught. Okay. See, it's just easier not to work with limits. All right. I've got this, and I'm going to have that equal to what? I'm going to have that equal to this. Like that. And that means that my current as a function of time is this exponential. Come on. And this looks a lot like the capacitor did, right? Whoa. Okay. So this looks like a lot like the capacitor did. So I as a function of t is what it started at, its initial value, times this dying exponential with a time constant in it like that. So if I take a look at the graph of this as a function of time, which I apparently can't do because this, oh God. All right, can we please move this thing? Okay. The graph of which is likely not a shock to you, starting up here at I naught, okay, and it's proportional to an exponential, e to the minus t over tau, where tau is going to be what's called the half-life, well, it's the time constant. It's not called the half-life, it's called the time constant. It's the time that has elapsed after the amount of current. The amount of current has dropped by 70% or so. All right, so you kind of reach the half point, the not the half point, the 70%, the 70 point. Anyways, that's what that looks like. That's what you could call the de-energizing of the inductor. It uses up all the energy that it had stored in pushing current to try to keep the flux going. Ultimately, it can't because it runs out of energy. Note that this is exactly the same type of thing as we found in the capacitor when we looked at the discharging of a capacitor. So the discharging of an inductor and a discharging of the capacitor are basically the same in a DC setting. Go back up to the circuit here. You'd find that if I took the L out and stuck a C in there, the same type of analysis would work. When you charge the capacitor up, okay, well, let's do this. When you charge the capacitor up, let's look at the DC characteristics of these two circuit elements. All right, so the capacitor initially, so if it starts uncharged, okay, let's suppose that it's starting in a completely empty state. Excuse me. So at t equals 0, when I put a switch on to and the switch has a circuit with a battery and a resistor in it, exactly like this other one over here, which had the inductor in it. Right at t equals 0, what does the capacitor do? It does absolutely nothing because there's nothing in it, right? All it's doing is it's acting like a piece of wire, as if it's not even there. Now, as time goes on and the battery continues to try and push charge, I'll just say as t goes off to infinity, the capacitor eventually acts like what? As the capacitor becomes fully charged, what happens to the current in that branch? It acts like a brake, acts like an open circuit, like you've turned it off, right? You have stopped current from flowing in that branch with the capacitor in it. I guess you might also suppose that the wire is like a short circuit. It's like a short. Initially, it acts like there's nothing there. Okay, if we look at the inductor, and likewise, it starts with nothing in it. At time equals 0, what does it do? What is it acting like? So when I shut the switch to the battery, let's go back over here and look at the circuit where I've got the inductors. Now suppose that I have drained the energy out of the inductor with the switch in this position. And now I'm going to put the switch into this position, right? So the inductor was drained, and now I'm going to bing, hit it again with the battery. What now is the inductor going to do as the battery attempts to push charge in the direction that I have here? What is the inductor going to do? Okay, let's just get rid of these. The inductor is going to act like, hey, quit that. It's going to push back. It's doing the opposite of what the capacitor did. It's acting like a block. In this case, because it has acts like an open circuit. It kind of acts like it does. It acts like an open circuit in that it doesn't let current flow initially. But I could say the same thing for up here. Essentially, the charge on the capacitor builds up to the point where the voltage is reverse. It stops the current from flowing. It's like acts like a reverse battery. Stop. So this acts like a reverse battery. Initially, personally, that's how I like to think of it, because an open circuit is something that is hard to recover from. And the time behavior of the inductor is such that it's going to act like this only for a little while. Just when the switch is clicked on, it's gonna initially push back really hard and then slowly back off. Okay, so as time goes on off to infinity and the steady state gets established, this acts like a wire. There's nothing to do. The inductor kicks only when there's a change. If you're in steady state, it doesn't care. It just has current flowing through it, and it's a piece of wire. So you can see that these things are basically opposites of each other. Their DC behavior is completely opposite. And so when you think about the currents, they're falling off, or they're going up, or the voltages are going down or up, and things like that. You can use the same type of thinking for the inductor as you do for the capacitor, I guess is my point, right? You just have to flip where you're thinking of it. Okay, the capacitor, I'm going to put one more column in here. If this thing is ever going to move, I'm going to put one more column in here on energy storage. The energy storage of the capacitor, we already know it stores energy in the E field. And its energy density is related to the square of E. So it's something like, that's the energy density inside a parallel plate. Let's see. I don't know why I even bothered trying to move this screen. Okay, that's energy density. All right, you probably remember that. And here it stores it in the B field. And I believe no, I probably should not be writing this down. That might not be right. I'm gonna have to go back and figure this out. I think that's I don't trust that. I don't know if that's necessarily right, but there's a magnetic energy density also that you can derive for the B field. Maybe I'll do that in a later video, but right now, just know that there's an energy density in the same way that the electric field has one in the capacitor. Okay, I think that is basically all I wanted to do here. Oh, actually, one other thing. The charging, I guess I can go through the charging characteristics of the inductor real quick here. The charging characteristics of the inductor, kind of as we, and I say charging in a completely wrong way. So this is kind of the discharging inductor. And again, I use that in the wrong way. It's the, yeah, I don't know what to call it. So that's what I'm going to call it, because I can't think of another word right now. So for a charging inductor, whoa, too bad, that's what we're getting. For a charging inductor, what does the graph of I versus T look like? Remember initially, as I don't want to go back and scroll up because it's going to take 5 minutes, but if you remember that circuit, it had, when I connected the battery to the resistor, the inductor initially has the reverse polarity of the battery and has the voltage of the battery in order to completely stop the current. So what happens here is that the current initially is 0 when I close the switch and slowly builds up to a value, which I think is this. No, it's the one above it. This one is this one, I naught. So it builds up to its steady state value, because after it has reached its steady state value, it acts like it's not there. Okay. So once the battery and the resistor have come to, okay, this is the current that we're going to have, and the resistor has said, okay, that's the voltage divided by the current. I mean, sorry, the voltage divided by the resistance. The inductor plays no more of a role, and so it charges up. And so you could probably see this is proportional. I think this thing, like, I thought it had a pretty good nap last night. This thing is proportional to something like 1 minus e to the minus delta t over L over R. Like that, right? So as time goes off to infinity, this exponential dies off and it becomes the steady state current. Okay, like so. And that's exactly what happens to the voltage of a capacitor. Right? If I change this to voltage, the capacitor would be becoming fully charged. The current would be dropping down to 0. As I look at the voltage of the inductor, the voltage is dropping down to 0 in steady state, and the current is going up to its max value. So that's what I mean. They're kind of opposites. The current and the voltage, just pay attention to what the characteristics are of these things in their DC settings, and you'll be fine. All right, so good. I think that'll do it for now. I'm going to go on and make an AC. We're going to start an AC circuit video on whenever the next day is. So that I hope that you enjoy a little bit of AC circuits. And for those of you taking Engineering 15 in the spring, we can at least get you a little bit of a start, though not as much as we normally would have. And that'll finish us up for this week. A little bit more on AC circuit, a little bit on AC circuits, and just a little bit of a finisher up on the Maxwell equations to kind of round it all out. Okay, stay sane, everybody.